Okay, in the last lecture, we started with the P block, we started with the group 16, we started with the oxygen. Yeah, we looked at little bit of acidic strength. I guess this was the last page where we stopped. Yeah, where we stopped in the last lecture. This was the, we did both of the class assessment in the last lecture, if I'm not wrong. Yeah, so we are on track with the class assessment also. Okay. Shalo, let us now. Today is the fourth lecture of P block. I have assigned some 7 lectures if I'm not wrong. And don't worry about question. Probably one lecture of 2 hours or 2.5 hours. I'll be taking only questions. Okay. Just like your chapter assessment. Before chapter assessment, I'll take a lecture of only questions from the P block, where you have to, again, it will be kind of a chapter assessment only, but there will be no chapter assessment as such. But in that lecture, you have to study and come. Okay. Since it is a huge chapter, I might take one more lecture just to revise everything and to, to do the questions. Okay. Shalom. Let us begin. So group 16 we have already started. With group 16, the first element, yes, the first element in the group 16, we know it is oxygen. Yeah, we started with the studying of the acidic character. So as we go down the group, what happens to the acidic character? Does it increase acidic strength? Will it increase or decrease? As we go down in the group, yeah, H2O, all this H2S, H2Se, H22E, H22E, sorry, H2TE, yeah, H22E. So acidic strength, does it increase or decrease? Yeah, what happens to acidic strength? Presently, and acidic strength, Sarjana, will it increase or decrease? Okay, simple question. Tell me, what is an acid? What is an acid? Let us understand by logic. Let's not mug up. Let us try to understand by acid. What is an H plus? What is an acid? Prashant, Sarjana, and like how do we define acid? Perfect, Sarjana. Okay, do not tell me in terms of electron. Perfect, and yes, Prashant, how do we say that? Okay, this is an acid. I write a compound. I will write a compound, and you will say yes, this is an acid. Okay, this is a base. How do we decide it? Okay, this is an acid. So simple. According to Arrhenius has given us one definition that anything that gives you H plus, anything that gives you H plus is your acid. Okay. Now tell me, what do you mean by strong acid and weak acid? Yeah. Is it acid which take protein shape? Yeah. Is it a strong acid? Yeah. Acid on steroids will be strong acid. What do you mean by strong acid? How do we define that this is a strong acid, this is a weak acid? What do we mean by strong acid, Prashant? Okay, perfect. Very good. And Sajna, how do we say it is a strong acid? Perfect. So acid is something that gives you H plus. So one that is strong acid or a good acid will give H plus easily. Simple as that. More amount of H plus will be donated. So over here, if someone asks you about acidic character of compounds containing hydrogen, what you have to check? You have to check, will your compound give H plus easily or no? That is what you have to check. Simple as that. Simple as that. For example, if I compare H2O and H2Se or H2TE. Okay, H2TE. Suppose I compare. Okay, now tell me which one will give H plus more easily. Okay, which one will give H more easily? Yeah. What is the criteria over here? So I have OHH. Okay, I have OPEHH. Okay. So you have to check which bond will break easily. Which bond will break easily? The one which, the bond which breaks easily will give you the H plus beta. Simple as that. The bond that breaks easily will give you H plus beta. Are you getting it, everyone? So you have to check which bond will break easily. Will the HO bond break or will the HTE bond break? What do you think? Come on, tell me. Will the option A or option B? Which bond breaks easily? Option A or option B? Yes, Prashant, Sarjana, correct, and Bhuvaneshwari, Akhilesh, Gopinath, Sindhuja, come on, tell me which bond will break easily? Your option A or option B? Is that HTE? Which bond will break easily? Sajna says HO. Come on, Prashanti. Everyone, I want your input. Come on, think about it. Use logic. Okay, there is a logic behind it. There is a logic behind it. One person says A, that does not mean everyone has to say A. One person says B, that does not mean everyone has to say B. Okay, use your own logic. Think about it. Which bond will break easily? Which bond will break easily? Very good, Sindhuja. Very good, Sarjana. Okay. So I have mixed answers. Okay, I want to understand the logic behind it. Okay, why did you answer that? Okay, if you have guessed it, then also fine. Okay, first you go. Sarjana, tell me, what did you thought of it? Like, did you guess it, or why HO bond will
Sir,
break
no,
more
sir. I
easily?
thought because oxygen is something electronegative, so it will
Okay,
pull electrons
correct,
toward itself, so the bond will
correct.
be broken easily, sir.
Okay, the bond will become more polar and H plus will be lost. Okay,
Yes, sir.
okay. Then Sindhuja, come on, you tell me why you think
Sir, in
B.
oxygen, double bond is present,
No, not
and
double
in
bond.
T,
No, 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 no double bond logic. I'm just talking about OH bond. Okay, there is no double bond over there. Okay, HOH and TEHH. Okay, there is no double bond over there. Where do we see a double bond? No double bond. I'm just asking this single bond OH, single bond TEH. Like which one will break better? Yes, Sindhuja. Okay, Sindhuja used the double bond logic. Fine, I got it. Which is not to be accurate. Okay, then tell me, and why did you say B?
Sir, I thought like T has a huge size, so it will be harder for it to hold on to both the heads, so it will be breaking easily.
Okay, very good. See, look over here. So I understand perfectly. Very good use of the logic. One logic which I really liked was the polarity logic. Okay, electronegativity logic. That okay, oxygen is more electronegative. Okay, I like the both of the logic. I'll tell you which is the correct one. Okay, oxygen is more electronegative. So what will happen? It will tend to take electron more towards itself. So it will make this H little bit weaker, and it will go as H plus. Okay, so that is one logic. Then Anne has used the logic H and TE. The size of TE is larger. It cannot hold a H. So this will break easily. See which logic is correct. First of all, both of the logic is correct. But which answer is correct? That is what we want. Okay. Which answer is correct? Both of the logic is correct. Now the answer that is correct is B. That is HTE. Why? Sajna, why this answer is correct? Look over here. The answer this is correct because okay, you use all your concept, electronegativity, electropositivity, enthalpy, entropy, whatever you want to use it. But first thing is look at the size difference. Okay, I'm just giving you the size difference. Your H is 1s, correct? The last electron in the 1s. Oxygen, which your last electron enters in which shell? Which subshell? Not shell, which subshell the electron enters? For hydrogen, it enters in 1s. Yes, Anthony. For oxygen, your last electron enters in which subshell? Prashanti, which subshell? Sindhuja, and which subshell? Your last electron enters in which subshell? Yeah, last electron enters in which subshell? Anthony, are you getting it? Last electron enters in which subshell of oxygen? Is it 1s, 2s, 2p, 3p, 4p, 4s? What is it? Yes, Arjuna, it enters in. Anthony, it enters in p subshell, that is 2p. That is 2p. So it is 1s is getting overlapped by 2p. Okay, 1s, 2p overlap is there. When you go down after oxygen, what do we have? We have sulfur. So it will be 1s, 3p. Correct. After sulfur, I guess we have selenium. Correct. So 1s, 4p. Okay, then we have tellurium, 1s, 5p. Okay. Hydrogen is this much, oxygen is little bit larger. Okay, they are holding it each other. Okay, your oxygen is this much, tellurium is, sorry, your hydrogen is this much, tellurium, if I compare, it is this much. Even if I make a bond, can your ant Not an, sorry, I'm talking about ant. Okay, can your ant hold up an elephant? Is it so? Yeah, no, it cannot. So forget about all of the other concept, electronegativity, whatever it is not able to hold it only properly. Are you getting it? Your ant and elephant stories, there are so many stories, oh my god. So your ant is not able to hold up that elephant itself. That has to be separated. That has to be separated, no matter what logic you use. So obviously 1s2p hybrid overlap is good, better than 1s5p, correct? This will break. Are you getting it? And hence this will be gone away more easily as compared to the hydrogen that is attached to the oxygen. Is it clear, everyone? Come on, give me yes or no. Is it clear? Yeah. Where did we go? Okay. So, where did we go? So that is why, what is happening? Acidic strength, if you go down the group with H2O, H2S, H2SE, H2E, acidic strength increases. Is it clear? Hence, thermal stability decreases. That means if I give little bit of heat to H2TE, it will break more easily. So thermal stability is very less. If I give the heat to H2O, the thermal stability is more as compared to H2TE because oxygen is holding hydrogen more better than the TE. Is it clear? Reducing character increases because it is giving H, obviously. So it gives H more easily. Reducing character increases. Simple as that. I hope it is clear. Yeah. Can we go ahead? So bond distance, bond angle, everything is fine. Let us go ahead. Now let us go to the reactivity with oxygen. Look over here. Reactivity with oxygen. Now your compounds when they react with oxygen, we are talking about group 16. Okay. So I'm not going to talk about oxygen reacting with oxygen. It is also possible you will get ozone if I react two oxygen together. Okay, I will get ozone. But let us keep it aside. From sulfur, if I react with oxygen, what do we get? We get the oxides. Obviously, if I react anything with oxygen, Anthony, yeah, why are you so upset today? Anything happened? Yeah, why are you sitting so sad in the class? I want some happy faces. Yeah. So oxygen, if it reacts with anything, Anthony, what will form? If it reacts with antimony, it will form antimony oxide. Yeah. Similarly, if it reacts with anything, it will form a oxide. Okay. Antimony, we have antimony also. Yeah. We have antimony, periodic table as antimony. So if it reacts with antimony, it will form antimony oxide. Same. If it reacts with anything, oxygen reacts with anything, it will form oxygen. Oxide. But sulfur, look at the sulfur. Yeah, sulfur has so many variable oxidation state. For example, SO3, what is the oxidation state of sulfur over here? Yes, everyone calculate. Anthony, calculate. Oxidation of sulfur over here in SO3. SO3, the oxidation state of sulfur. Correct, Sindhuja. Anthony, come on, calculate. Correct, Sajna. Correct, Anthony. What will be the oxidation state of sulfur in SO3? Yeah, I have to take sulfur as X. Single oxygen is -2. How many oxygen we have? We have 3 oxygen. So 3 into -2, it is -6 is equal to 0. So X is equal to +6. X is equal to +6. Okay. So if you see from +2, +4, +6, come on, calculate for S2O3. Come on, tell me the oxidation state of S in S2. Yeah. Tell me the oxidation state of S in S2O3. Oxidation state of S in S2O3. Correct, Bhuvaneshri. Correct, Anne. Correct, Sarjna. Correct, Sindhuja. Yeah. In from +2, +4, +6 to even the odd numbers like +3. Yeah, like +3. So these are the variable oxidation states. +3, correct question, +3. So sulfur, it can go into variable oxidation state. Okay. Similarly, tellurium, over here 213 is written, it is wrong. Actually, it is SeO2 and SeO3. Okay, it should be SeO2 and SeO2. Okay. So or it forms, basically if oxygen reacts with this compound, it forms oxide, and in the exam the question can come on sulfur. It can form variable oxides. Okay, variable oxidation state. Now let us see the reactivity with oxygen. Yeah, reactivity with oxygen. Look over here, everyone. So reactivity with oxygen, reactivity with oxides. Okay. So your oxides, okay, I'll come to this. Wait, your oxides, they basically act as an oxidizing agent. Simply, yeah. Now, for example, SO2. Now, come on. According to VSEPR, I hope everyone knows VSEPR. Booster, so we have done VSEPR. But apart from that, I hope everyone remembers VSEPR. How many of you remember? Raise hand. VSEPR. VSEPR. Yes, come on, tell me. How many of you? No one? Okay. So according to VSEPR, tell me. I'll tell you for SO2, you have to tell me for SO3. Okay, I have SO3 also, I guess. I have SO3 also. So I'll tell you for SO2, you tell me for SO3. Okay. According to VSEPR, how do we calculate? Sulfur. Okay, I'm going to calculate hybridization state, Anthony. Okay, so sulfur. How many valence electrons are there in the sulfur, everyone? It is just below oxygen. So how many valence electron, Anthony, in the sulfur? Yes, in the sulfur. How many valence electron? How many valence electrons in the sulfur? Sindhuja and Bhuvaneshwari. How many valence electrons, Prashanti, in the sulfur? Tell me for oxygen, it is just below that. So to the whole group, it will apply the same. Yeah. So whole group, it will apply same. For oxygen, how many valence electrons are there? In the shell. In the shell. Correct? And yes, in the shell, not subshell. In the shell. Bhuvaneshwari, in the shell, not 2p2. I am not asking subshell. P is the subshell. Shell is your K, L, M. Those are your shells. Yeah. So it is 6. It is 6. So what I'll do, everyone, I'll draw those 6 electron, Anthony. 1, 2, 3, 4, 5, 6. Okay. I have 2 oxygen, 1 oxygen. Sindhuja, how many bond does it form? You have told me already. Akhilesh, 1 oxygen. It forms how many bonds? Yeah, everyone. 1 oxygen forms 2 bonds. Okay, so it will acquire 2 electrons. So 1 oxygen, that is 1 bond pair. Second oxygen, oxygen, oxygen. Remaining 2 electrons are your lone pair. So what is the number you are getting? Bond pair plus lone pair, that is a hybridization number. Okay, so I have 2 bond pairs of oxygen plus 1 lone pair, that number is 3. So you have to start from the S. Anthony, you have to, number is 3, you have to start from S. So if the number was 2, it would have been 1S, 1P. If the number is 3, it will be S, then 2 are left, so sp2. If the number is 4, it will be sp3. So P is over after that. If the number is 5, it will be sp3d. I hope everyone is getting it. Yeah. If the number is 6, it will be sp3d2. Okay. So what is the hybridization over here, everyone? The number is 3. The hybridization is sp2. Is it clear, everyone? Come on, give me yes or no. Come on, give me yes or no.
Sir,
Yes, Anthony.
sir, can you explain this again?
Okay. So Anthony, look over here. What we have is the sulfur, correct? So I have carbon, nitrogen, oxygen. Okay. So to the whole group, we have the same valence electrons. Okay. For carbon, the valence electrons are 5. So whole group of carbon will have valence electron 4. Sorry, not 5, 4. Nitrogen, we have 5. So the whole nitrogen group, we have 5. Oxygen is 6. So whole oxygen group will be 6. So your sulfur is in oxygen group. What is our compound? Sulfur dioxide. So 6 electrons I have drawn. 1, 2, 3, 4, 5, 6 electrons. To that 6 electron, we are now forming bond. 1 oxygen forms 2 bonds. Correct? So 2 bonds means 2 electrons over here. So 2 electrons of oxygen, 2 electrons of sulfur. So 2 electrons of sulfur, 1 oxygen bond. I have 2 oxygen. So 1 more oxygen bond. That means I have now 2 oxygen bond pairs. Okay. Then remaining 2 electron I have is the lone pair. Correct. So that 2 bond pairs I have written over here. 1 lone pair I have written over here. 2 plus 1 is 3. So that number is important. According to that, we will decide the hybridization. Who after adding bond pair plus lone pair, Anthony, it is sp. If number is 3, sp2, you have to increase 1. If the number is 4, sp3. If number is 5, increase 1 more. Now p is exhausted. P, there are only 3 orbitals. Next we have is the d. So number 5, sp3d. Number 6, sp3d2. Number 7, sp3d. Yeah. Okay. Now sp2. What is the geometry for sp2? Yes, Anthony.
Yes, sir. Clear, sir. Thank you, sir.
What is the geometry for sp2, Bhuvaneshri? And geometry for sp2, Prashanti? I am asking geometry, okay, not shape. What is the geometry for sp2? Come on, tell me. Your carbocation geometry, sp2. Geometry for sp2. Yeah, sp2 geometry. Linear. How it is possible? No, I'm not asking SO2 Sarjana. I'm asking sp2 hybridization. Okay. sp2 hybridization, if it is, then what is the geometry? Okay. It is not linear, correct, Bhuvaneshri? It is trigonal planar. It is trigonal planar. That's why your SO2 is like this. S over here. Okay. A double bond O, and this lone pair. Okay. It makes a triangle. So this is a planar and we call it as a trigonal planar. Is it clear, everyone? Yeah, give me yes or no. Is it clear? Okay. So sulfur, just like a phosphorus, is in the P4 form. Oxygen is in O2 form. Similarly, sulfur in the nature, generally it is in the acid form. Okay. So if I react acid with oxygen, I'll get the sulfur dioxide. Simple. That is how we prepare it. Okay. Next we have, and one more thing. Now this was a VSEPR, which is more accurate actually for finding out the hybridization of non-metals, but we also something called as VBT. Okay, we have something called as VBT. Okay, now VBT, we draw the orbitals. Okay, for the VBT, we draw the orbitals. Okay, for the VBT, we draw the orbitals. Okay, now look over here. So what happens in the VBT? Now of the SO2, little bit of actually there is a little bit of what we say exception over here. There's a little bit of exception over here. I'll tell you what. Okay. So over here, I will draw the sulfur ground state. If you draw the electronic configuration of sulfur, the valence will be 3s2, 3p4. Yeah. The valence will be 3s2, 3p4. Then you have 3d. Okay. Then you have 3d0 empty. So I have drawn the ground state. Now I have to form bonds. So oxygen, one oxygen forms 2 bonds. 2 oxygen will form obviously 4 bonds. So I need 4 vacant orbitals. I need 4 half-filled orbitals, not vacant. It is a covalent bond, 1 electron from sulfur, 1 electron from the oxygen. So what happens? As the oxygen come close to it, 1 electron jump over here. 1 electron jump over here. Now understand this Prashanti. In the VBT, we only consider those orbitals, in which the sigma bond is there. In this, there is a sigma electrons. Okay, in this there are sigma electrons. For example, in the oxygen, okay, for example, I have this. How many sigma bond I have? How many pi bond I have in this? Okay, or I have SO2. Let us say SO2, and tell me for SO2, how many sigma and how many pi? Yeah, how many sigma and how many pi? In SO2, suppose this is my structure. Okay, how many sigma, how many pi I have? Yeah. How many sigma, how many pi? Prashanti, Sarjana, Kevin, come on, tell me. It is fine even if it is wrong, we are learning. we have, correct, we have 2 sigma, we have 2 pi, correct. This is sigma, this is pi. Similarly, sigma, pi. Getting it? Sigma and pi. So 2 electrons which enter in this, we call them as sigma. 2 electrons, we call it as pi. That's why it is p pi d pi, p pi d pi written. Are you getting it? And we only consider the sigma electron. So over here, we'll only consider this S and this 2p. That's why for the VBT, also we call it as sp2 hybridization. Is it clear? It will be more clear when we do the SO3. But is it clear till over here, everyone? And Sajna, Prasanski, Bhuvanashri, is it clear till over here? Yeah? Is it clear? Yes, Prasanski, give me yes. Is it clear? Yeah? Sindhuja, is it clear? Anthony, is it clear? How do you say yes in Tamil? How do you say yes in Tamil? M. Is it M? Ama. Is it Ama or is it M? What is it pronounced with? Am. Am. Is it pronounced as Am or Ama? Am? Ama. Okay. Bye. Chal. Ama. Okay. Okay, so let us go ahead. So give me Ama. Is it clear? Ama. Okay. And no is Illi. Illa. Illai. I know the name. Illai. Illai. That I know. Okay, so if it is clear, Ama or Illai. Okay. Chalo. Let us go ahead now. SO3. Okay, you do it for SO3. Come on, tell me the hybridization SO3 and tell me the geometry. What do I want is bond pair plus lone pair. Do not tell me hybridization. Tell me bond pair, how many bond pair, how many lone pair. 1 plus 1, 2 plus 1, 3 plus 1, 2 plus 2, whatever it is. According to VSEPR for SO3, come on, tell me for SO3 now. Tell me for SO3, bond pair plus lone pair. Come on. Bond pair plus lone pair. Bond pair plus lone pair. And you do not consider each of them individual separate. Okay. Those are together. Oxygen, what you are calculating, they are together. Okay. Very good, Sarjana. Yes, Prashansky, Anthony, come on, you have understood VSEPR. Come on, tell me now. Sulphur, draw the electrons, join the bond, tell me how many bond pair, how many lone pairs. Yes, given we have no. Ragul, see, understand this. Look over here. Look over here. Look over here. Over here, I have considered, I have used 2 electrons, but I will consider them, they are forming bond with only one element, no? So I'll consider them as a 1 bond pair, not the 2 bond pair. Okay, so do not get confused. This is 1 bond pair. I have used the word 2, no, alphabet 2, the numerical 2, because this 1 bond pair, 2nd bond pair, and 1 lone pair. Is it clear? So similarly for SO3, calculate. Very good, Bhuvaneshri. Correct, Anthony. Correct, and is it clear? Do not say 6. It is not 6. Okay, it is forming bond with only one atom or one element, so we will call it as 1, not the 2. Okay, so SO3, I'll come to this resonance structure. SO3, yes, it is forming sp2 because 3 bond pairs, 0 lone pair. Oxygen, oxygen, oxygen. Oxygen, oxygen. Again, it is not sp3, sorry, again it is sp2. 3 plus 0, the number is 3. For number 3, Anthony, it is sp2 hybridization. It is sp2 hybridization. Yeah. So for sp2 hybridization, it is what? For sp2 hybridization, again it is trigonal planar. Now this time we do not have lone pair. We do not have lone pair. Okay. So trigonal planar. Now one more important thing, understand this, geometry and shape are two different things. Geometry and shape are two different things. For example, let's come back to SO2. Okay, in the geometry, as I told you, it is trigonal planar. Okay, but in the shape, what is written over here? What is written over here? Bent or angular. That is because when we talk about shape, we do not consider the lone pair. Okay, I will draw this geometry, trigonal planar. I'll erase the lone pair. That will be my shape. Okay, in the shape, please remember, write it on the top of your book, Anthony, that for the shape, draw the geometry and erase the lone pair. Draw the geometry and erase the lone pair. We do not consider lone pairs in the shape. We just consider the elements and the atoms. Is it clear? Come on, give me Ama. Yeah? Is it clear? Okay, fine. Okay. So let us go ahead now after this. So for SO3, the geometry and shape both are same. For SO3, geometry and the shape both are same. Okay, for geometry and shape both are same, both are trigonal planar. Now look at this. This perfectly explained the VBT. What we were trying to explain in the our SO2. This is perfectly explained over here. Look over here. So for sulfur, again it is what? 3s2, 3p4, 3d0. According to VBT, yes, this is the valence electrons. Okay. So now we have to form SO3. That means we require 6 half-filled orbitals. Yeah, 1 electron each, 6 half-filled orbitals. So what will happen? This will jump over here. This will jump over here. Yes, for the excited state, 1 electron jump to the D of S, 1 electron of P jump to the D. Correct? So we have got our excited state. So each of them, we have 3 oxygen, 1 sigma, 1 pi. Correct? So 1 sigma over here, 1 sigma over here, 1 sigma over here. Next we have pi, pi, pi. And that is why, as I told you, we only consider for the BBT, we only consider the sigma bonds. So sigma till over here. So what do we have? sp2 hybridized according to BBT. Is it clear? Come on, give me yes or no, or Amma or Ilai. Yeah. Come on, give me Amma or Ilai. Yeah. Is it clear, Ragul?
Sir,
Is it clear?
sir,
Yes, Anthony.
sir, why 3 sigma bonds and
Because Anthony, when you form a multiple bond, so whenever you form a multiple bond, for example, if I have, let us say H2O, okay, Anthony, so H, okay, so when you form a single bond, we call it as a sigma bond. Similarly, suppose I have CH4 or I have carbon-carbon single bond, okay, this is a sigma bond. But when I increase a bond, let us say I make a double bond. So one will be sigma and one will be pi. One will be sigma, one will be pi. When I increase one more, then it will contain 1 sigma and 2 pi bonds. Okay. So similarly, Anthony, what we have over here, we have SO3. So here SO3 is something like this: oxygen, oxygen, oxygen. So each sulfur and oxygen contain a double bond. So one is a sigma, one is a pi. One is a sigma, one is a pi. Anthony, are you getting it? One is a sigma, one is a pi. Is it clear, Anthony?
yes, sir.
Yeah, is it clear?
Yes, sir.
Oh, you are welcome. This time you did not say thank you. It is fine. I am joking. Okay.
Thank you,
No
sir.
need to say thank for that. Okay. Chalo. Let us see the chemical properties, yeah, of group 16. So these reactions, I guess I have a table. Just a minute. Let me check. No. Okay. So look at this reaction with oxygen. These are 3 important reactions. Okay. Write it down. I want you to write it down. Okay. Your sulfur trioxide. How do we form? This is a kind of preparation for sulfur trioxide. Okay. So if I have a sulfur dioxide, see, simple. If I have a basic sulfur, if I oxidize it, I'll get sulfur dioxide. If I continue the oxidation of sulfur dioxide using any catalyst, I'll get the sulfur trioxide, correct? So SO2 plus O2, SO2 plus O2, sulfur dioxide plus oxygen, that is a sulfur trioxide. Come on, tell me, what do we mean by oxidation in the organic terms? What do we mean by oxidation? Yeah, in the organic terms, what do we mean by oxidation? Yeah, everyone, what do we mean by oxidation in organic terms? Not inorganic, I'm saying for organic terms. Oh my god, this English language, I do not know why they have named it as inorganic. I'm saying for organic, when we study organic chemistry, what is oxidation in that? Okay. This electron terms is for inorganic chemistry. I am talking with respect to organic chemistry. Yeah, I am talking with respect to organic chemistry. I do not want in terms of electrons. I want in terms of atoms and elements. When I say oxidation, what change happened to your reactant? If I say this is an oxidation reaction, that means what? How do I identify that yes, this is an oxidation reaction? Yes. So simply when we do the oxidation, what happens? Either oxygen is added or the hydrogen is removed. Either oxygen is added or the hydrogen is removed. That is why I am saying over here the oxidation of sulfur dioxide, because to the SO2 oxygen is getting added and it is becoming SO2. Is it clear, everyone? If you check it with respect to electron also, then also it will be same. For example, SO2, what is the oxidation state? Rakul and Prashanti, what is the oxidation state of sulfur over here in SO2? Yeah. What is the oxidation state of sulfur? Correct. It is +4. It is +4. What is the oxidation state of sulfur in sulfur trioxide? Come on, give me. What is the oxidation state of sulfur in sulfur trioxide? Correct, Ragul. Ragul, come on, tell me. Sulfur in sulfur trioxide. It is. Yes, Ragul. It is. It is +6. Yeah. So +4 to +6. That means loss of 2 electron. It means yes, loss of electron. Our known loss of electron is oxidation. Yeah. So loss of electron is oxidation. So yes, this is an oxidation reaction. Is it clear, everyone? Is it clear? Yeah. Now similarly, H2SO4. Now remember this P4O10. Where do we use P4O10 or your dilute H2SO4? Okay, where do we use it? These are your dehydrating agents. Okay, even concentrated H2SO4. These are your dehydrating agents. What do you mean by dehydration? Yes, these are your dehydrating agents. What do we mean by dehydration, everyone? Yeah. What do we mean by dehydration? Perfect removal of water. So I have H2SO4. So if I remove H2, if I remove O, what is left? SO3. So dehydration of H2SO4. Are you getting it? Ragul and Sarjna, Anthony. Yeah. Yes. So Prashanti, are you getting it? Okay. So your H2SO4, if I do the dehydration, yeah, reacted with oxygen, it will undergo dehydration. If I heat it, so what will happen again? I will get SO3. Similarly, if I do Fe2SO4 thrice, if I do the same thing, yeah, if I heat it, your sulfur trioxide gas will be evolved. Sulfur trioxide gas will be evolved. Come on, write down this three reaction and tell me done, done, done in the chat box. Come on, go ahead. Write down the three reaction, important reactions. Sure. Done, done, done. Come on, write it down. Akhilesh, Vipinath. Okay. Now, see, again, an important thing. Over here, I know you will remember the oxidation state, you will remember the oxide. What is important is to remember the name. Remembering name is very difficult. Remembering name is very difficult. Yeah. If I give you any molecule like H2O7, okay, if I ask you what is oxidation state, you will simply tell me +7. Yeah. If I give you H2O3, yeah, if I give you H2O3, if I tell you to calculate oxidation state, which you have already calculated it, yeah, you will easily tell me +3. You will do it. I have no doubt in that. But if I tell me the oxidation state of sulfur sesqu oxide, will you be able to do it? No. Yeah. So that is why your name is important. Sulfur sesqu oxide. Yeah, it is nothing but H2O3. So this is where you have to remember the name. This is where you have to remember the name. See, suboxide. That means what? Your oxygen is less than sulfur. Suboxide. Okay. So sulfur is dominant. So H2O. Monoxide we already know. Dioxide we already know. Trioxide, yes, we know. Heptoxide, yes, we can know. Tetroxide, it is fine, we will understand. What is to remember? Write it down on the top. Sulfur suboxide and sulfur sesqu oxide. Someone write on the top. S2O is the sulfur suboxide. H2O3 is the sulfur sesqu oxide. Now, do not get confused with the sulfur heptoxide. SO7 is impossible to form. No one can form 14 bonds in the element. Yeah. So obviously it is H2O7. Okay, the sulfur heptoxide. Otherwise, you will tell me sulfur heptoxide. We had calculated for SO7. So do not go there blindly. Use some logic also. Yeah. So SO7 cannot exist. It is H2O7. Are you getting it, Prashanti? Yeah. So write down on the top sulfur suboxide and sulfur sesqu. I always struggle to pronounce this word. Sulfur sesqu oxide. I'll say it slowly. Sulfur sesqu oxide. I hope it is clear. Yeah. Done. Come on. Done in the chat box. Write down on the top. See this small thing you should write down on the top of your book, so that when you will revise, it will be easier for you. Yeah, when you will revise, it will be easier for you. Okay, chalo. Let us go ahead. Now reactivity with halogens. Reactivity with halogens. Now, one more thing.
Sir,
Again use your logic. Again use your logic. Okay? Again use your logic.
sir, excuse me, sir.
Yes, Anthony?
Sir, can you show the last slide again, sir?
Yes, write it down, Anthony. Anthony, do not write everything. Just write sulfur suboxide and sulfur sesqu oxide. I hope, okay, one more question I wanted to ask. I hope everyone is able to get the note of it. Yeah, the PDF format. Kindly check, because some of the students, okay, my personal one-on-one students has complained it to me that they are not able to see the PDF format of the what we are doing over here. Okay, the PDF format of notes, they are not able to get it. There's some technical glitch, so I hope it is not happening with you all. Yeah. Did you try to access it, or you did not even try it for the revision? I know you have not tried it. If you have not, so kindly check that also after the class. Okay, if it is not coming, then kindly WhatsApp the team, trouble them. Anthony, is it done?
Yes, sir, done, sir. Thank you, sir.
Yes, Anthony, is it done?
Yes, sir.
Okay, sure. Okay. Now again a simple logic. Again a simple logic. Let us go ahead. Again a simple logic. Now we are doing the group 16 now, reactivity with halogen. Suppose I have any elements. Okay, I have any element. For example, oxygen, I have taken O. Okay, so I have OF2. Let us say I have OF2. Okay, now again using the same logic, tell me if I go down the group, the bond stability, which one will be more stable if I go down the group? Yeah, if I go down the group, will the stability decrease or increase? What do you think? If I go down the group with respect to halogen, using the same logic, okay, A more easy question. Suppose I have HF and HCl. Which is a stronger acid? Sarjana, Prashansky, and Antony, Kirtini, you are late. 1 hour. Rakul, which will be a stronger acid? HF or HCl? Which one will be stronger acid? HF or HCl? Using the same logic. HF or HCl, which one will be the strong acid? Yes, Prashansky, Sarjana, which one will be the strong acid? Yeah? Yes, Ragul, I got it. No need to write it in the caps. Yes, Sarjana, which is a strong acid? Is it HF or HCl? Using the same logic. Same logic it is. Same logic. HF or HCl. Prashansky, HF or HCl. Using same logic. Sarjana, what did I tell you? Same logic means what? Again, the size. Size logic again, you have to lose the H. Yeah, what is an acid? Acid means H plus is given away. H plus is given away. After I explain the concept, Prashansky, you are saying the answer. H plus is given away. So size of HF is quite similar. 1s2p, 1s3p is weaker. This will break more easily. H plus will go away more easily. So HF, in reality, HF is a weak acid. HF is not even a strong acid. Okay, your HCl, HBr, HBI are your strong acid, and HF is a weak acid because it does not dissociate easily. Okay, why did I explain you this? Because look at the stability. Okay, as you go down the group, the stability decreases. With the halogens, the stability is decreased. Is it clear, everyone? Come on, give me yes or no. Is it clear? Yes. And you will study this SF6. It is, write it down, it is exceptionally stable. It is an octahedral structure. Fluorine is small. Yeah, they have a very good bonding. Yes. So it is exceptionally stable. Okay, exceptionally stable. Your SF6 is exceptionally stable halide. Okay, most stable halide you can consider SF6. Okay. Okay, so these are all the halides that are formed. These, as I told you, see, learning P block, I will teach you and I will go. Okay, but it is in your hand how many reactions you do it after the lecture. Okay, after the lecture, if you do not revise, or maybe tomorrow, okay, if you do not revise, if you do not write down the reactions again in a separate book, it is impossible to study in organic. Now, in our PPT, I have included all of the reactions, including your NCRT, including your reference book, including everything. Okay, so I have covered already everything. So you have to write down those reactions. If you do not write it, you will not be able to do it. Okay, so kindly write it. So these are all of the halides. See, sulfur, your monohalides, oxygen, sulfur, selenium. Okay, they are able to form monohalides. Your tellurium, polonium, due to the exceptional size, they are not able to form monohalides. Okay, then you have dihalides like F2, Cl2, Br2. Okay, SF2, SCl2. Then you have tetrahalide, in which your oxygen cannot form. Hexahalide, no, it cannot form. Okay, so these are some of the halides of your group 16 elements. Okay, should we take a break? What is the time? 8:59. Okay, you all deserve a break. I know this is a little bit theoretical. So I want everyone back by 8:08. We'll start sharp at 8:09. Okay, kindly be back. Do not do late because we have to complete this. Okay. Come on, back in the chat box. Are we back? Come on, back, turn on the cameras. Ragul, Anthony, Arjuna, Shalom, come on. Just a minute. Shalom. Let us go ahead. We have done S2, S2, S2 oxide. Okay. Now let us do the preparation. Okay, so first we are doing the preparation of oxygen. Okay, after doing this, let us prepare some oxygen. Yeah. First of all, tell me naturally from where do we get oxygen, Prashanti? Yes, Arjuna, where do we get the oxygen from the natural ways? Obviously, we take the oxygen. Yeah, isn't it? From plants, yeah, isn't it? From plants, yeah. I guess we discussed that experiment, no, where I asked you about the fish. Yes, where we discussed that when we boil the water and when we put fish into it, we discussed that, correct? So even fish, yeah, even fish, they breathe in the oxygen, isn't it? They breathe in the oxygen, but it is just they do the respiration through the dissolved oxygen, what is there in the uh, water. Okay. Now we breathe in oxygen. Obviously, that is what we get from the nature. So you know, in the commercial method, when we have to do commercially, we have to take the oxygen. For example, for oxygen cylinder, correct? Oxygen cylinder. There are various uses of oxygen for the person who is suffering from the low oxygen levels. Yeah, we give the oxygen to them. Then the mountain climbers, yeah, mountain climbers, they carry the oxygen with them because there is a less oxygen in that, correct? In the aeroplanes it is there so that, you know, if anything by chance anything happens, so that mask comes down of the oxygen mask, correct? So that oxygen what we have, okay, we prepare oxygen also from the nature by taking the oxygen from the nature, from the atmosphere. Okay, so that is what we prepare on the large scale. Now in the small scale, in the lab, we cannot take it for like that. So in the lab, how do we do it? In the lab, for the small scale, we take the oxygen rich compounds where the oxygen is maximum. Like for example, potassium permanganate, for example, potassium permanganate, for example, potassium chloride, for example, potassium nitrate. I just heat them. Now heat it in the absence of oxygen. Okay, just heat them. So when you heat them, what will happen? Obviously, if it is something oxygen rich, if I heat it, it will release oxygen gas. It will release oxygen gas. Are you getting it, everyone? Yeah. Just a minute, everyone. Just give me a minute. Is it clear, everyone? If I have something which is oxygen rich, if I heat it, yes, if I heat it, it will release oxygen, isn't it? Yeah, yeah. So if I heat potassium permanganate, oxygen gas is released. Again, potassium perchlorate, oxygen gas is released. Again, potassium nitrate, oxygen gas is released. Yeah. Similarly, again, dioxides, peroxide, higher oxides. In other language, they are also oxygen rich. Yeah. Come on, give me example of peroxide. Everyone, give me one example of peroxide. Prashanti, Sarjana, and give me one example of peroxide. Give me two examples of peroxide. Give me two examples. Give me two examples of peroxide. The molecular formulas. Give me two examples of peroxides. Okay. The molecular formulas. Molecular formulas. Molecular formulas. Molecular formulas. Okay, one is your hydrogen peroxide. That, yes, I know most of you will tell me. One is your peroxide salt also, sodium peroxide, yeah, you can use it, Na2O2. Okay, so when I say peroxide, yes, what is the peroxide linkage? Can anyone tell me? What is the peroxide linkage? Yeah. What is the peroxide linkage? Very good, Bhuvaneshwari. Even BaO2 is a peroxide. So give me, what is peroxide linkage? What do we mean by peroxide linkage? Yeah. What do we mean by peroxide linkage? What is a peroxide linkage? Yes, anyone? What is the peroxide linkage? Yeah. What is the peroxide linkage? Each atom will be linked to oxygen atom. See, not exactly. See, oxygen atom, peroxide means what? Your O, O. Okay. This linkage, O single bond O. O single bond O, for example, if I have H2O2, so it is H. If I have sodium peroxide, O minus minus Na plus Na plus. Okay. So this O linkage, Prashanti, this O linkage, write it down. We call it as what? Peroxide linkage. This is a peroxide linkage. Okay. So again the same thing, by heating dioxides, by heating peroxides, by heating higher oxide. That means what? They are oxygen rich compound, like mercuric oxide. Yes, like mercuric oxide. If I heat it, again oxygen is released. Silver oxide, manganese dioxide, all of them are oxygen rich. So kindly please understand this now, but after the lecture or tomorrow when you will revise, please write down these reactions again just to remember it. Okay. Look over here again. Lead tetroxide, lead dioxide, barium peroxide. Yeah, barium peroxide. Yes. If I heat them, see, oxides means what? Over here, barium oxide. So I have Ba2 plus O2 minus. Correct? O2 minus. What is barium peroxide? I have O minus, O minus. Both of them are stabilized by Ba2 plus. Are you getting it, everyone? Yeah. So that is how they are stabilized. So this is again peroxide linkage. That is why this is a barium peroxide. Yeah, barium peroxide. Okay. So again they are oxygen rich. If I heat them in the absence of oxygen, oxygen gas, oxygen gas, oxygen gas. Simple as that. That is how you prepare it. Again, look over here, hydrogen peroxide. If I heat it in presence of any catalyst, what will I get? Again, the oxygen gas is released. Now that is what, how you prepare in the laboratory. Okay. So same thing is written over here. I have taken perchlorate, I have taken peroxide. In detail it is written. Basically everything is telling you what does it release. It releases the oxygen gas. It releases the oxygen gas. Now this industrial preparation, how do we prepare on the large scale? Yes, how do we prepare it? Simply, how do we take it from atmosphere? Yes, oxygen gas is there in the atmosphere. What is the maximum? Which gas is maximum? Yeah, presence in the atmosphere. Ragul. In the atmosphere, which gas is maximum? Yeah, which gas is maximum, everyone? In the atmosphere, which gas is maximum? Yes, correct answer. Ajna Prashansi, come on, tell me. Fine, even if it is wrong. Open up. Ragul, Anthony, Akhilesh, come on. Which gas is maximum? Which gas is maximum? Which gas is maximum? Carbon dioxide. Is it so? No. It is nitrogen, more than 70%. Okay. So in our atmosphere presence, we have various gases. Nitrogen, we have oxygen, we have carbon dioxide, various gases we have. So what we do the fractional distillation. Okay. By using fractional distillation, we liquefy that and we separate the oxygen. Okay. So how do we prepare it? First is your fractional distillation. Okay, first is a fractional distillation. Second is the electrolysis of water. If you remember in the electrochemistry, if I have taken off yours, if you remember in the electrolysis of water, yeah, if we do the electrolysis of water, one of the byproduct was again oxygen. So remember, for the industrial preparation, What we have from our fractional distillation, write it down, industrial preparation for the dioxygen or the oxygen. First is fractional distillation of air, correct, and second is the electrolysis of water. So from air and water we get the oxygen for the large scale purpose. Electrolysis of water. Electrolysis of water. Come on, write down. Preparation, industrial preparation. First is the fractional distillation of air. Fractional distillation of air. Second is the electrolysis of water. Second is the electrolysis of water. Come on, done in the chat box. Done. Can we go ahead? Yeah. I guess this PPT is now broadcast coming up. Okay, so now we have the dioxygen chemical properties and the physical properties. Okay, so physical properties, obviously oxygen is colorless, tasteless, odorless. Yeah, oxygen is colorless, tasteless, odorless. Imagine if there was any color to the oxygen. Yeah, we are breathing in all of the color. Yeah, plants are giving all of the colorful. Our environment will be full of colorful, isn't it? Yeah, so it is not colorful, we know it is colorless. Then it is tasteless, obviously oxygen is tasteless, and it is odorless. Yeah, now if you are catch up with the news, yeah, in the Delhi, yeah, you must have seen our climate was horrible. Not now, now it is monsoon season, so all of the pollution what was there was washed out. Yeah, but in Delhi, you know, the climate, it was so horrible. It was so horrible. Yeah, you know, there is one company who sell you the oxygen. Imagine, now that is a time that they were selling the oxygen, that for half an hour and 1 hour for a good oxygen you have to pay money. Yeah, so that day is not very far, so you have to plant the trees. Tell me honestly, how many of you have bought some trees anytime in your life? Raise hand. Anyone? Did you bought a plant or something anytime in the life? Raise hand if you have done it. Okay, Anne has done it. Prashanski. Okay, Anthony has done it. Sarjana? No? Okay, Prashanski has also done it. Sarjana is feeling left out. Okay, so she has also raised the hand. She has also done it. For how many days did it survive? Yeah. For 15 minutes, sir. It survived only for 15 minutes. Yeah. It survived only for half an hour. For how many days did it survive? Yeah. It's a tree. Oh my God. Where did you plant it, and when did you plant it? That it has become a tree. Oh my God.
So once when I was in 6th, sir, and then again in 8th. In Kerala, in my hometown, I was planting jackfruit, the rambutan and neem trees, sir. It's still there.
Nice. Okay. Nice. So you should plant trees. Yes, Prashansi, for how many days did it survive? Rajna? Yeah. You know, in our school when I was young, we had a project. We had a project where we had to plant a tree, and we had to make, like, well, not a tree, sorry, plant in a pot, and we had to show them, yes, after a week or 2 weeks, yeah, we have got this. Uh, it is there. I planted in my 8th standard. I do not believe that. Presently, I do not believe that. That you had planted in an 8th standard and it is still there. In the next lecture, you will bring it. Okay, bring it on your head. Okay, and sit in the class. Not a plant, it is a tree. Wow, my God. Nice. We have so many people with so many students who have planted a plant and now it is a tree. Nice. Impressive. Okay. So you have to continue with it. Okay. Now let me tell you mine also. Okay. So what I do is on Sundays we have a, what we say, We are a group of friends who plant trees across the Mumbai. Okay, so even I do that, and few of my plants, yes, they have survived, and now they are growing into trees. So you should also do it. Okay. So dioxygen basically point is colorless, tasteless, and odorless. Okay, now oxygen. Tell me, is it its solubility, is it high or low? In the water, oxygen. In the water, oxygen. Will it be highly soluble or will it be less soluble? What do you think? Okay, solubility will be high or low. In the water, oxygen solubility is it high or low? Come on, my fish people, tell me. The solubility of oxygen in water, is it high or low? Yeah, come on, H or L. I am talking at room temperature. Is it high or low at room temperature? At room temperature, the solubility of oxygen in water, is it high or low? Yeah, tell me. Prashansi, Rajna, Ragul, Gopinath, Bhuvneshri. Yes, solubility of oxygen, is it high or low at room temperature? In water, yeah, first of all, oxygen is not highly polar. Okay, it is slightly polar. It is not highly polar molecule. Okay, okay, because you have two same elements attached to each other. Okay, so you can consider it as a non-polar also. Okay, so the solubility is low. The solubility is low, but but it is just sufficient so that our aquatic life survives. Okay, imagine. Okay, like this nature is so beautiful. Like everything is crafted to the perfection. Our human body, it is so complex. So many processes are happening at the same time. It is so complex, but it is crafted to perfection that everything happens on its own. Even same is the nature. Yeah, yeah, aquatic life. Oxygen solubility is not very high, but fish require only small amount of oxygen to survive. So that oxygen which is dissolved, it is sufficient for the fish. How beautiful our nature is. Yeah. So yes, it is slightly soluble in water. Basically, the solubility is low. Okay. Slightly soluble in water. It can be liquefied to a pale liquid under pressure. Okay, it is liquefying at 90 Kelvin. So if you liquefy it, you have to decrease the temperature to liquefy it. Obviously, it is a gas, so you have to decrease the temperature to liquefy it. So it liquefies at 90 Kelvin. Okay, three stable isotope: oxygen 16, oxygen 17, oxygen 18. Okay, is it clear, everyone? And it is slightly soluble because it is paramagnetic. Okay, it is paramagnetic. It forms oxides. Yeah, strongly exothermic. Not required. Now look at this. Now I'm not going to take each and every reaction from this. See, simple logic. Simple logic. If we react anything with oxygen, what do we get? Yes, if we react anything with oxygen, we get simply oxides. Yeah, we get simply oxides. So if I react cesium with oxygen, sorry, it's not cesium, it is calcium. Okay. If I react calcium with oxygen, I get the calcium oxide. If I react aluminum oxide, phosphorus with oxygen, phosphorus oxide, carbon with oxygen, carbon dioxide, zinc with oxygen, zinc oxide. Yes, carbon oxidation, again carbon dioxide. Yeah, sulfur oxidation, we have seen sulfur dioxide, oxidation, sulfur trioxide. Yeah, so simple logic is whenever you react oxygen with something, what do you get? Oxide. Yeah, that is the basic logic. If you follow that, you will get every reaction correct. Is it clear, everyone? Yeah. And hydrocarbons, if I react with oxygen, what do we call it? For example, this combustion. What do we call it? Combustion. Yeah. Is it clear, everyone? Yeah. Come on, give me yes or no. Now next we have are the uses. Now uses again, uses. So simple uses. Obviously normal respiration is there, combustion is there. Yeah, for combustion in oxyacetylene welding, combustion of fuel, oxygen cylinders, manufactures of metals, steel, etc. Okay, sure. This is done. Okay, so now we have completed our last lecture today. Okay, next we have is our this lecture today. Okay, let's do one thing. Take more 5 minutes break. Okay, go drink water, wash your face if you want. Okay, we'll continue after 5 minutes. Okay, I'll start with the new compound ozone. There are few reactions which I want to discuss that we'll discuss afterward. First, let us complete our compounds. Okay, let us do ozone first. Okay, let us do ozone. Take a 5 minute break, wash your face, drink water, and come back. We'll continue at 8:36. Okay. Come on, back in the chat box. Come on, turn on your camera. Question speak. Arjuna and Anthony, Chemistry. Yes, are you back with a complete focus? Yeah. Okay, sure. Now let us go ahead with the ozone. Yeah, ozone. Come on, tell me what is the molecular formula for ozone, everyone? Ozone. What is the molecular formula of ozone? Yes. Perfect. And what is the use of ozone? Correct, Ragul? What is the use of ozone, Ragul? Yeah, what is the use of ozone? What it does and where is it present? What it does and where is it present? Prashansky? Protection. Yes, protection, but what? Uh, protection for the earth, from the earth. Protection for the earth, yeah? So, so ozone is a very notorious person. What happens? Someone tries to attack the earth, like aliens, ozone send them back, isn't it, Prashansky? Sorry, Sadhana? Yeah? It protects it means what? How does it protect us? Does it protect us from the aliens? Yeah, does it protect us from the falling stars? From what does it protect us? And is it in atmosphere? Is it inside the atmosphere? It protects us from the UV rays. Yeah, it protects us from the UV rays, correct. So it filters out. It filters out the UV rays. It filters out the UV rays. Yeah, it filters out the UV rays. Correct. So yes, it filters out the UV rays. Perfect. It filters out the UV rays. Otherwise, what will happen? What will happen if ozone does not exist? Yeah. What will happen if ozone does not exist? Yeah, what will happen? What will happen if ozone does not exist? Yeah. What will happen if ozone does not exist? There will be no one to protect us. But what will happen? How will it harm us? Yeah. See, it is like when you search anything on the Google, like which will destroy everything means what? Okay. Like for example, if you search, you have headache, you have this on the Google. What does Google tell you? What disease you have? Yeah, you are having pain in your hand. You have everything. Yeah. So what does Google tell you? You are suffering for what? Never. I am telling you, never ever search with your symptoms to the Google. Okay, because Google always and always tell you one thing: you have the cancer. No other disease. Google will straightly tell you: you are having headache. Okay, you have cancer. There is a pain in a leg. Okay, you have a cancer. Cut it off. Yeah. So don't search symptoms on the Google. Okay, so it will destroy organisms means what, and it will give us cancer. Okay, like UV rays are so harmful that what will happen now? The rays are not getting filtered out. Yeah, UV rays are coming with the sun. So if my hand is continuously in that UV rays, what will happen? It will destroy the cell. It will hit my hand and it will start multiplying the cell. Yeah. So obviously I will get the cancer. It will start dividing the cell. I will get the cancer. Yeah. So there are some places you can search it on the Google afterwards. Ozone hole, where there is a ozone hole. Okay. That means what? Ozone is so disturbed over there that ozone is literally not present over there. Okay, so if you go to such places, there is a high chances of getting skin cancer. Okay, there is a high chance of getting a skin cancer. Is it clear? Ozone is nothing but O3. Ozone is O3. Yes, so how do we prepare ozone? So there is a way to prepare pure ozone is by the oxygen. Okay, if I react oxygen, this is what I was telling you. If I react with oxygen and oxygen, I get the ozone. I get the ozone. Yeah, the electric discharge means what? We are using H mu. Yeah, we are using H mu. We are giving the electric discharge, and O2 is getting converted into O3. Yeah, is it clear, everyone? Chalo, let us go ahead. Let us go ahead. Okay. Now O3. Okay, we are with the ozone. Now ozone, the color is pale blue color, pungent odor. Okay, read it afterwards. Boiling point 385, melting point 24 Kelvin. Yes, it is diamagnetic in nature. Okay, concentration of above 100 ppm. It is harmful. Yeah, ozone is actually harmful, and the ozone which is present above atmosphere, how does it get depleted? Prashanti, why does it get depleted? Why does it get depleted? Yeah. Why does it get depleted? Sarjana and Ragul. Yes, Bhuvaneshwari. Why does it get depleted? Ozone, why does it get depleted? Because of CFCs. Yes, excessive use of CFCs. Yeah. The chlorofluorocarbons that are given out by refrigerators, the air conditioners, correct? So excessive uses of CFCs is the reason for your depletion of the ozone. Okay, sure. Now properties of ozone. Ozone is neutral in nature. It is neither acidic nor basic. Hence, if I do the litmus test, your blue will remain blue, red will remain red. There will be no change in the litmus paper. So your ozone is your neutral in nature. Ozone, if I do the electric discharge, I will get the oxygen. Now also it also acts as, obviously there is an excessive of oxygen presence C. So ozone, write it down, it will also act as an oxidizing agent. It will also act as an oxidizing agent. Obviously it has excess of oxygen, so it will act as an oxidizing agent. Ozone will also act as a oxidizing agent. Okay, it will also act as an oxidizing agent. Okay, now for example, look over here, lead sulfate. So it will convert all of your sulfides. If I do the oxidation of sulfides, all of the sulfides, lead sulfide, zinc sulfide, copper sulfide, whatever you have, if I react it with ozone, write it down, sulfides plus ozone will give you presence C, it will give you sulfates. Okay, sulfide plus ozone, it will give you sulfate. So remember, whatever sulfide you have, and if there is a ozone reaction, if I have copper sulfide, yeah, if I have copper sulfide, it will convert it into copper sulfate. Okay, so all of the sulfides get converted into sulfates. Okay, then halogen acids to corresponding halogens. Halogen acids to corresponding halogens. For example, if I have HCl, if I react it with ozone, yeah, if I react it with ozone, what will happen? Your chlorine gas will come out. Yes, your chlorine gas will come out, and the ozone will combine. The ozone will combine with the hydrogen. Okay, ozone will combine with the hydrogen. Okay, so what will happen over here? Write it down if you want. If I react HCl, if you want a reaction, I'll write it. Look over here, everyone. If I have HCl and I react it with ozone, what will happen? Your chlorine will come out. Yeah, chlorine gas. Your halogens will come out. Oxygen gas, one of the preparation, and you have H2O. You have H2O. So if I have to balance it, balance. Come on, write down the reaction. If halogen acids, this is your halogen acid, HCl. Cl is a halogen, correct? HCl is an halogen acid. So HCl, if I react it with ozone, what will happen? The chlorine gas will be liberated, oxygen gas will be liberated, and water is released. Yeah. Are you getting it, Prashanti? Yeah. Okay. Similarly, Ki, 2I2. Ki, 2I2. Yes. So it is oxidizing everything. It is oxidizing everything. Okay. Then ozone, again, it is acting as an oxidizing agent. So it will oxidize non-metal. It will oxidize metal. No matter what you have, silver to silver oxide, mercury to mercurous oxide. Yes. Phosphorus to phosphorus acid, sulfur to sulfuric acid, iodine to iodic acid. It goes on oxidizing everything. Okay, ozone is a very strong oxidizing agent. It will oxidize everything. So all these are nothing but your oxidation reaction. All these are nothing but your oxidation reaction. Is it clear, everyone? Come on, give me yes or no. Is it clear? Is it clear? Yeah. And tell me, what is iodic acid, by the way? What is iodic acid? Anyone knows? If I say iodic acid, anyone? Iodic acid. And that's why I have used the word moist over there. That's why I have used the word moist iodine. Yeah. What is iodic acid? Yes, everyone. What is iodic acid? Yes. What is iodic acid? Yes, what is iodic acid? Yeah. No one knows? HiO3. Okay. HiO3 is your iodic acid. So iodine, if I react it with the ozone, yes, Why I have written moist? Because I require H from that. Okay, I require H from that. Okay, so if I react it, what I will get? I will get the iodic acid. I will get the iodic acid. Are you getting it, everyone? Yeah. What is the oxidation state of iodine over here? Can anyone tell me? What is the oxidation state of iodine in iodic acid? HiO3. Yes, what is the oxidation state? Come on, find out. Find out the oxidation state in iodic acid. Yeah, iodine oxidation state in iodic acid. Yes, it is +5. So 0 to +5, 0 to +5. Is it oxidation or reduction? 0 to +5. Is it oxidation or reduction? Yes. 0 to +5. 0 to +5. It is oxidation. It is oxidation. Kevin, why are you so late? Okay, it is oxidation. So moist iodine, that is what I am telling you, everyone, that your ozone is responsible for the oxidation of iodine. I hope it is clear. Come on, give me yes or no. Is it clear? Is it clear? Yes. Okay, so that was your oxidation of non-metals, oxidation of metals. Okay. Now similarly, it will oxidize metalloids also, arsenic to arsenic acid, antimony to antimony acid. Okay. Now, formation important. Formation of ozonide. This is there. I hope you must have done this hydrocarbon chapter in the 11th standard. Yeah, I do not expect you to remember everything. Yeah, but hydrocarbons. Yeah, what was that? It was ozonolysis. If you remember, ozonolysis. Yeah, if I react, for example, if I have CH3, CH, double bond CH2, if I carry out ozonolysis, Prashansky, Sarjana, and if I carry out ozonolysis, what do I get? Yes, if I carry out the ozonolysis, what do I get? Remember, everyone, if you remember, like your teacher must have told you shortcut also for that. Teacher must have told you a shortcut. Break the double bond, add something to the left, something to the right. Obviously, I was not there to teach you in the 11th, but your teacher must have told you the shortcut for it. Yeah. Ozonolysis. Yes. What is it? Yeah, what happens in ozonolysis? See, if you remember, in the ozonolysis reaction, whoever have taught you must have told you simple. Ozonide is a different thing. I'm asking about the final product. Okay, this ozonide, what you are seeing over here is an intermediate. That is what I'm going to tell you. Okay, I know the reaction is in front of you. Okay, I'm not asking about ozonide. It does not end over here. If I react and I do the hydrolysis, what happens? Over here, this breaks. This breaks. Oxygen, oxygen, it is there in the preparation of your aldehyde and ketone. Yeah, it is there in your hydrocarbon reactions, in the reactions of alkene. It is there, the ozonolysis in the hydrocarbons, reactions of alkene. So what do I get? CH3CHO, that is aldehyde, and the CH2O, that is also an aldehyde. Yeah, the formaldehyde. So what happens? How does it get added over here? If I have CH3CHO, what happens? I have CH3CHO, O, yes, over here, O over here. Yes, this is how it gets added, and finally, Prashansky, it breaks like this. Yes, this comes over here, this comes over here. Yeah, and this O is lost with H2. Yes, that is how you get the, and this is an intermediate, we call it as a ozonoid. So yes, ozone is used in the organic reactions to prepare the ozonoid also. Is it clear, everyone? Yeah, is it clear? Okay, sure. Then we have high actions with peroxide. If I react it with the peroxides, yes, of ozone and peroxide, what will I get? Simply, it will break the ozone, the peroxide linkage, okay, and you will get oxides and the oxygen. You will get the oxides and the oxide. Okay, again, if you are reacting with ozone, it is going to give you oxide. No matter you have non-metal, metal, if it is the work of ozone is to give you oxide. Simple as that. Okay, simple as that. Now, use of ozone. Yes, it is used in sterilizing of water. Yes, it is used as a germicide, disinfectant. Look at it for the purifying air, obviously, for the manufacturing of synthetic camphor. In the labs, we have discussed about the ozonolysis. Is it clear till over here, everyone? Yeah? Is it clear? Okay. So, let us go ahead. Let us go ahead. Now, tell me how many of you remember the phosphorus allotropes? Yeah? What were the phosphorus allotropes? Yes, what were the phosphorus allotropes? What were the phosphorus allotropes? Anyone? Phosphorus allotropes? No one? Sarjana, Prashanti? Yes, the red, white and black, or black, white, red, or white, red, black. Yeah, white, red, black. Which one was the most reactive? Which one was the most reactive? Those who have attended the last lecture. Yes, white, red or black. Which is more reactive? Prashanti, Sarjana? Yes, Raghul, which one is more reactive? It was white. Which one was more reactive? Reactivity white, red and black. This was there for the phosphorus. We have discussed about the phosphorus. Correct? Now similarly everyone, what do we have? We have the allotropes of sulfur. Okay. So write it down. We have rhombic sulfur, 3 allotropes again. Rhombic, monoclinic, or we call it as a plastic sulfur. Okay, rhombic is also called as alpha, monoclinic is also called as beta, and plastic is called as delta. Write it down. Rhombic, monoclinic, plastic. 3 allotropes of sulfur. 3 allotropes of sulfur. I'll come to the stability. First write it down. Rhombic, monoclinic, or plastic. Rhombic, monoclinic, and plastic. Okay. Rhombic sulfur, monoclinic sulfur, and the plastic sulfur. Okay. Now look over here. Rhombic sulfur and the monoclinic sulfur. Okay, look over here. Transition temperature. Okay, transition temperature. Look over here. So your rhombic sulfur below 369. Okay, understand this. Below 369 Kelvin, what sulfur you have? You have is the rhombic sulfur. Come on, write it down. Important. Rhombic sulfur exists below 369 Kelvin. Okay, rhombic sulfur exists below 369 Kelvin. Okay, and if I heat it above 369, it will convert it into monoclinic sulfur. Okay, it will convert it into monoclinic sulfur. So rhombic sulfur below 369, monoclinic sulfur above 369. Okay, above 369. And the plastic sulfur. Now you will ask me, what about plastic sulfur? So plastic sulfur is actually amorphous form. Okay, it does not have any proper transition temperature. Okay, plastic. What do you mean by amorphous? The amorphous solid. What do you mean by amorphous? What is the main difference between crystalline and amorphous? I have taken your. I remember I have taken your solid state. The first one, no, I have no. Okay, it was, I guess Vinayak sir was there for the solid state. No, no. Okay, got it. But still, you have to answer. What is the main difference between crystalline and amorphous? Yeah, 2D structure. What else? The main difference is not 2D structure. Come on. What else? Okay. There was one important word. Okay, irregular in shape. Okay. What else? Definite heat of fusion of whom? Amorphous or crystalline? Kevin, definite heat of fusion. Was it amorphous? That is what I wanted to hear. N isotropic. Who was anisotropic? Was it your crystalline? Was it your amorphous? Was it your crystalline? Was it your amorphous? Your anisotropic. Was it crystalline? Was it your amorphous? Anisotropic, Prashanti, Kevin, and who was anisotropic, Ragul? Was it your crystalline? Was it your amorphous? Yeah, anisotropy. It was crystalline solid which was anisotropic. That means it was in a perfect regular shape. So if I go in any direction, it will show me different properties. It will show me different magnetic and electrical properties. Yeah, and your isotropy means they were randomly arranged. So if I go in any direction, I'll get the same property. Yeah, I'll get the same property. Okay, so let us do the allotropes of sulfur now. Where were we? Stable at room temperature. Now this obviously below 369. Rhombic sulfur, insoluble in water but easily soluble in CS2, readily soluble in CS2. Kindly read it once. Okay. Next, what we have is the allotrope of sulfur, that is C6. How does it look like? Come on, tell me your imagination. First of all, let me tell you, it is a chair form. Apart from chair, what does it look like? Sir, it does look like a sleep. I want sleep. Yeah. What does it look like? To me, it looks like thunder. Thunder would have been more accurate, but it would be easy to remember. Thunder. Then what else? To me, it also looks like, what do we call it? What do we call it? We throw it and again it comes back to us. What do we call it? Frisbee? No, frisbee is the disc. That we throw it, it is kind of this shape. If we throw it hard, the boomerang. Oh my god, boomerang. Yeah, that looks like little bit. Looks like boomerang also, isn't it? So this is a chair form. Now you will wonder what kind of chair is this in the world. Is there any chair which exists like this? Yes, it exists. Yes, you must have gone to the movies. Yeah, if you have not, then there at least once you would have sat on the recliner chair. Yeah, you sit down in the movie, you push the button, it goes back, you relax. Yeah, isn't it? Yeah, you sit over here with your body, torso, then this, your legs, good stretch, and watching the movie, enjoying. Yeah, so it looks like a chair form, little bit. Okay, so S6 allotrope is actually look like a chair-like structure. It is having chair-like structure. Okay, it is having chair-like structure. Okay, it is having chair-like structure. S6 have a chair-like structure with the bond angle. Write down the bond angle is 102.2. Bond angle is 102.2, and the bond length is 205, double of that. Remember like this. 102 is a bond angle, double of that is a bond length, picometer. Okay, picometer. Is it clear till over here, everyone? Is it clear? Okay. Now let us go to sulfur dioxide. Should be. Okay. Now if I start the test, again some of the question you will not be able to do it because we have not reached over there. What we will do? Okay, let us do one thing. Just like last lecture, again we'll do the two class assessment in the next class together. Okay. And today I'll extend it till 9:20. Okay, I'll teach you till 9:20 and I'll leave. Okay. Okay. I'll not take the class assessment. Please stay. Okay, we'll not do the class assessment. Let us complete this and we'll do the two class assessment together again in the next class. Or if you want to do it, you can do it after the lecture. Okay. Fine. Come on, give me yes or no. So advantage is you might go early, 9:20, 9:20 to early. Okay. So sulfur dioxide, obviously the oxidation state. If I ask you of the sulfur dioxide, what is the oxidation state, everyone? Sulfur dioxide, what is the oxidation state? Yes, and Prashanti, Sarjna, Kevin. shows that we are sleepy. Yes, Arjuna? Oxidation state of SO2, not SO3. Prashanti, what is oxidation state of SO2? Oxidation state of sulfur in SO2. Yes, oxidation state of sulfur in SO2. Yes, Prashanti, sulfur, and has given answer. Anthony, Kevin, what is the sulfur oxidation state? Yes, sulfur oxidation state. Prashanti, how it is plus 6? Why you are all getting plus 6? Oh my god. Am I doing maths incorrect? X, oxygen is minus 2, 2 into 2. I hope it is 4 only. Yeah, minus 4 is equal to 0. That is plus 4. How it is plus 6? It is plus 4. Yeah, so the oxidation state is plus 4. Okay. So look over here. So preparation, if you do it one table, your whole preparation is done. So this is a general preparation. If you do the oxidation of sulfur, it gives you sulfur dioxide. If you further oxidize sulfur dioxide, it will give you sulfur trioxide. No rocket science. Okay. But in the laboratory, how do we prepare it? We prepare it by mixing Na2SO3 and N2SO4. Okay. It is Na2SO4, not N2SO4. Na2SO4. Okay. So what do we get? Yes, again sulfur dioxide gas is released. Similarly, sulfide acid combined, what do I get? Water and sulfur dioxide. So in the laboratory we have three methods. Again, I am taking acid and the copper. So copper sulfate and sulfur dioxide gas is released. Yes. But in the industries, look at this. In the industries, if I have FeS2, yes, your sulfide again react with oxygen, it will give you oxide. But in that process, it will release sulfur dioxide. In that process, it will release sulfur dioxide. Similarly, again, zinc sulfide, if I do the oxidation, it will give me oxide. But again, in that process, it will release sulfur and the oxygen will combine to give you sulfur dioxide. So one table, your whole preparation is done. Now look at the physical properties. It is colorless, toxic gas. Obviously, sulfur dioxide is toxic. Suffocating smell, heavier than air. Okay, we discussed about the gas which is lighter than air. Which one was it? Which gas is there in the balloon? Which gas is there in the balloon? Yeah, that goes. Yeah, which gas is there in the balloon? Some of you had answered me a very shocking answer that day. Which gas is there in the balloon? Prashanti, Sarjana, Kevin. Which gas is there in the balloon? Which gas? It is. Which gas is there in the balloon? Are no, you do not know. If you inhale that gas, if not inhale, like if you take it from the mouth, the voice changes, isn't it? The voice changer, it is helium. Yeah, helium is lighter than the air. That is why it goes. Yeah, helium is lighter than the air. Yeah. So see, I still love balloons. You can't judge me, but I still buy balloons for me also. Okay. So it's nice to have balloons. Okay. So helium is there in the balloon. Okay. Now what do we mean by lighter than air? That means if you leave it, yeah, helium gas balloon, it goes up in the atmosphere. Yeah, it does not stop. Yeah. So same, if I say heavier than air, that means if I have a balloon with the sulfur dioxide, it will go down. Yeah, it will not go up. Okay. Then it is soluble in water. Okay, liquefied at room temperature. Okay, these were the properties. Okay. Now let us do the chemical properties. Okay, sulfur dioxide. It is acidic in nature. Now look over here. Any oxide, remember, any oxide, how do we decide it is acidic or basic? Okay, what I'll do, I'll put that in the water. Okay, I'll put that oxide into water. Okay, non-metal oxide, I'll put that into water and I'll check what I'm getting. If I get acid, it is an acidic oxide. If I get a base, it is a basic oxide. Simple. Okay, and if it is amphoteric, then it will react with both acid as well as base. Okay. So over here I have sulfur dioxide. If I add it into water, what I am getting? I am getting H2SO3. okay, which is nothing but sulfurous acid. Yeah, although it is a weak acid, but still it is an acid, sulfurous acid. Correct? So yes, my SO2 is acidic in nature. We have just proved. That's why now it will react with bases. So I'll show the reaction with bases. For example, sodium hydroxide is a base. I reacted with SO2, which is an acid. What did I get? Sodium sulfite, which is a salt, and a water. Kind of a neutralization reaction. Are you getting it, Prashant? Yeah, base plus acid, salt and water. Same thing over here. Yeah, calcium hydroxide. I reacted with sulfur dioxide. What did I get? Calcium sulfate. Yeah, calcium sulfide. Sorry. Then we have, again, if I continue the reaction, I'll get the bisulfite. Yeah. So yes, what does it prove? All this reaction proves that sulfur dioxide is acidic in nature. Sulfur dioxide is acidic in nature. Yes, sulfur dioxide is acidic in nature. Okay. Now it is a non-combustible gas, but yes, when ignited with some substances, it extracts oxygen from it. Okay, that means what? It undergoes oxidation. So for example, sulfur dioxide, if I ignite it with oxygen, I'll get the sulfur trioxide. Yes. Okay, then we have what? It acts as a mild oxidizing agent. Okay, fine. Okay. Now reaction with halogens. Okay, this is also important. Reactions with halogens. Okay, so if I react sulfur dioxide with halogens, for example, Cl2, okay, it gives me sulfuryl halide. Now, what is the sulfuryl halide? It is like a thionyl chloride. Sulfuryl halide. Anyone? Sulfuryl halide. What is the sulfuryl halide? Come on, tell me. Sulfuryl halide. Yeah, sulfuryl halide. Anyone? Anyone knows? Okay, tell me. Thionyl chloride. What is thionyl chloride? Anyone? Thionyl chloride, anyone remember? SOCl2. Exactly same is a sulfuryl chloride. Okay, what happens? Only thing is you have one more oxygen. Okay, that is a SO2Cl2. Sulfuryl halide. So this is a sulfuryl chloride. Write down this reaction. If I reacted with halogen like chlorine, what it will give me? It will give me sulfuryl chloride. It will give me sulfuryl chloride. Okay, sulfuryl chloride. So what do I have? S. It looks like this. S double bond O, Cl. Okay, Cl. Thionyl chloride, you do not have an extra oxygen. In the sulfuryl chloride, you have an extra oxygen. Simple. Okay, is it clear? Come on, write down the reaction. Tell me done in the chat box. Come on, focus. Last 10 minutes. Focus. Come on, write it down and done in the chat box. Okay. Doing. Okay. It acts as a reducing agent. Your sulfur dioxide acts as a reducing agent. Why we are saying reducing agent? Because it is, if I react it with oxygen, Sajna, it is undergoing oxidation. Yeah. And what is a reducing agent? Reducing agent is the one which undergoes oxidation. Simple as that. Okay. So here are some of the reactions which proves that it is a reducing agent. What is a reducing agent, everyone? Yes, what is a reducing agent? Prashanti, Sajna, and what is a reducing agent, Kevin? Gopinath, what is a reducing agent? Reducing agent means what? Reducing agent means, yes, reducing agent means it itself undergoes oxidation. It itself undergoes oxidation but reduces other. So yes, we have seen reactions, so many oxidation reactions where SO2 is getting reduced. Simple as that. Okay. It is it is undergoing oxidation, but it reduces the other. Yeah, that is a reducing agent. So strong reducing agent in presence of moisture. Okay, presence of moisture. So potassium dichromate to chromium sulfate. Yes, what is a potassium dichromate, everyone? Potassium dichromate. Yes, what is potassium dichromate, anyone? Come on, tell me potassium dichromate. Yeah, potassium dichromate. Yeah, is it chromate? K2Cr2, KCr2O7, what is it? No one knows. Potassium dichromate. Come on. Potassium dichromate. Check. Do trial and error and tell me potassium dichromate. Potassium dichromate. Come on. What is potassium dichromate? Yeah. Question C, Sadhana. What is potassium dichromate? Yeah. That is K2Cr2O7. Okay, so if I take K2Cr2O7, okay, I react it with your sulfur dioxide. Correct, Kevin? What do I get is a chromium sulfate. Okay, what do I get is a chromium sulfate. That means it is Cr2, okay, Cr2SO4 thrice. Cr2SO4 thrice. Okay, Cr2SO4 thrice. Okay, chromium sulfate. Okay, chromium sulfate. Now chromium sulfate, okay, chromium sulfate, if I have, what is the oxidation state of chromium over here? Chromium sulfate. What is the oxidation state of chromium? Can anyone tell me? What is the oxidation state of chromium over here? What is the oxidation state of chromium? Yeah. Oxidation state of chromium. Yes, tell me. Oxidation state of chromium, no one knows. Shocking. Alright. Do not have to do the X method. No. It is your ionic compound. What are you doing? It is your ionic compound. Why are you doing the X method? Question is Sadhana. And it is an ionic compound plus 3. Your SO4 is minus 2. Cr plus 3. That is succeeds. Are you getting it? Okay. Now your X method you use it for this rule. Tell me oxidation rate of chromium in K2Cr2O7. Come on. Tell me the oxidation state of chromium in K2Cr2O7. For Cr2SO4 triacylinders, it is what? It is plastic. It is a head. Tell me K2Cr2O7. Tell me the oxidation rate of single chromium. Tell me the oxidation state of single chromium. Come on, calculate all my iron minds. Calculate the oxidation state of chromium. Calculate the oxidation state of chromium. Come on, I want an answer from everyone. Last answer I am asking to you all. Don't worry. Correct, Karen? Yes, question C, Sadhana. What is the oxidation state of chromium in K2Cr2O7? Ragul. What is the oxidation state of chromium? Sadhana, what is it? Chromium over here. Take K as plus 1 if you are having confusion. Take K as plus 1. Yeah. So it is 2 plus 2x minus 14 is equal to 0. Correct. So 2x is equal to 12. X is equal to plus 6. X is equal to plus 6. So plus 6. Okay, what we have is a plus 6 to plus 3. Is it oxidation or reduction? Plus 6 to plus 3. What is it? Is it an oxidation to reduction? Is it oxidation or reduction? Come on, tell me. Yes, correct, Kevin. Prashanti, Sarchna, and plus 6 to plus 3. Is it oxidation or is it reduction? Yeah, is it oxidation or is it reduction? Yes, perfect. It is a reduction. So what does this prove? That it is undergoing reduction. That means what? Who is responsible? Your SO2 is responsible. So your sulfur dioxide is acting as a reducing agent. Yes, I hope it is clear. Yes or no? It is reducing your chromium from plus 6 to plus 3. Yes, I hope it is clear. Prashant Steve, is it clear? So all of this reaction tells you all of these reactions. Okay, potassium permanganate to manganese sulfate, potassium iodine to iodine, iodine. Yeah, Ki. If I react with SO2, yes, it will give me I2. Okay, it will give me I2. Okay, again, it is going from -1 to 0. So again, it is proving that SO2 is what? SO2 is my reducing agent. SO2 act as a reducing agent. Okay, SO2 act as a reducing agent. Okay, fine. Chalo, let us stop it over here. From the next class, we'll continue where I will left. Okay, just rely on this. We'll start in the next class. Okay, now I want you all to listen, revise kindly. Okay, you have this as a PPT, PDF. Kindly write this reaction. I have taken everything from the reference book, NCERT combined, everything is there. Okay, so please write down the reaction with yourself, solve some question. If you are not able to do that, please ask me, I'll help you. Okay, but you have to do self study. If you do not do the self study, it is of no use. Your 2 hours sitting for lecture, 2.5 hours is literally waste. So kindly do the self study. Is it clear? Yeah, Prashansky, is it clear? Okay. So let us stop it over here today. Yeah, everyone. Okay. Thank you for your time. We'll do the 2 class assessment together in the next class. Okay, do not worry. Chalo. Thank you for your time. I'll see you in the next session.